start the recording. So in today's lecture, what we are going to discuss is the frequency response of an op-amp. Now, what do we mean by frequency response? We already know that an op-amp can provide you a gain of, let's say, A, right? So you have this electronic device which can provide a gain of A, which will be if your input or the difference of the input at the positive and negative terminal is BA, and the output, what do we expect? We expect A times B, right? So that's the gain of the op-amp. And again, keep in mind, all of these are AC quantities. At the input, you have an AC input voltage, at the output, you have an AC input voltage. You also need to provide the DC biasing points as well, which will come to later. Now, if you assume that this op-amp has a gain of A, does it mean it provides gain of A for all AC frequencies? We have already mentioned that, okay, you have an AC input, right? That means it has some kind of frequency. It could be 1 hertz, it could be 100 hertz, it could be 1 gigahertz. Does it provide the same gain for all different frequencies? The answer is no. Why? Because you already know that the op-amp has a finite output resistance. Right? We are calling this RO. That you have a finite output resistance. Now, at any point when you are designing a circuit, there would always be parasitic capacitance. So there are parasitic capacitances at the input side, there are parasitic capacitances at the output side. So let's just say that you have a parasitic capacitance over here, and let's call it Cout. Let me see if I have a different marker over here. Apparently not. Yeah. So you have this circuit that, okay, you are providing some voltage. Again, let's assume that you have a voltage source over here. You have a resistance, which is this resistance RO, and you have a capacitance of PO. What is this circuit? Does this circuit do some kind of filtering? And many of you already know about this, that, okay, yes, this circuit works as a low pass filter. Why does it work as a low pass filter? Because if you write down the transfer function, what is defined as the transfer function? The ratio of your output quantity to the input quantity. And let's say you are taking your output quantity over here, V0. That's your output. That's the same thing you are taking here, right? V0. It's the same point as this. Now, if this is your V0, if this is your V out, like there are multiple names to call the same quantity. Some books call it V0, some books call it V out, but it's basically the output voltage. Now, what is V0 over Vs in this case? You already know how voltage division works, right? Voltage division would be the impedance of this capacitance and the impedance of that resistance. That will determine what would be the voltage division between these two quantities. Now, what is the impedance of a capacitance? You already know it from your circuits 1 or circuits 2 classes, that for any capacitance C, the impedance is 1 over j omega C, where omega is the angular frequency and C is the value of that capacitance. Similarly, if you're talking about an inductor, the impedance of an inductor is j omega times L. So this is the device that you are working with, an inductor or a capacitor, and the impedance of the inductor or capacitor is either j omega L or 1 over j omega C. Now, in Laplace domain, some of you are also very familiar with Laplace transform. So in Laplace domain, you represent this as S times L. Basically, S is your j omega. S is equal to j omega. And that's the Laplace term that you consider when you are doing any kind of Laplace transform. So if you do the same thing here, this becomes 1 upon SC. So for a capacitance, the impedance is 1 over j omega C or 1 over SC. So that's the impedance of this capacitor as a function of the frequency. So now you can write down what would be the voltage division. What would be the voltage division between this capacitor and that resistor? That voltage division between the capacitor and resistor would be 1 upon SC in the numerator divided by 1 upon SC, or let's call it SC naught, because we are calling this capacitance as C naught. So 1 upon SC naught plus R naught. That's the voltage division. That's our transfer function. So your V naught over Vs is equal to the impedance of the component across which you are taking the output divided by the impedance of that component plus the impedance of the other component. Yeah, it's basically R2 divided by R1 plus R2. Same formula that you have learned in lecture number 1. So the formula is nothing different. It's just that you're taking the impedance of the capacitance instead of taking an impedance of a resistance. And impedance of a capacitance is 1 upon SC. And that comes from the Laplace transform equations, which we are not going to cover in this class. We're assuming that you have already covered it in your circuits 1 and circuits 2 class. Now, if you do the calculation now, in your numerator, you will have 1 upon SC naught. In the denominator, you will have 1 plus SC naught R naught. Or let's call it SR naught C naught. SR naught C naught divided by SC. Right? That's what you can write in your numerator and denominator. So your 1 upon SC naught in the numerator and denominator gets cancelled. What you are left with is 1 divided by 1 plus S times R naught C naught. That's the transfer function of this RC circuit. Now, why are we saying that this is a low pass filter? We're saying that this is a low pass filter because just assume that your frequency is 0. And let's say you are plotting the transfer function as a function of the frequency or the angular frequency, which is omega in this case. Omega is equal to 2 pi times F. But F is the actual frequency. Omega is the angular frequency, high school physics. So omega is equal to 2 times pi times F. We are plotting the transfer function with respect to the omega or the 2 pi F term. And remember that J times omega is your S. J times omega is equal to S. Now, if you are just, of course, you understand that this is a complex quantity right now, because if we replace S with J omega, you will have 1 divided by 1 plus J omega times R naught C. So you have a real term and a complex term. But let's say what you are interested in is the magnitude of the transfer function. So if you are interested in the magnitude of the transfer function, what you can say from this equation, that when your S is equal to 0, when your S is equal to 0, which means your omega is equal to 0, that means you are at 0 frequency. S is 0, omega is 0, F is 0. That is, you are at 0 frequency. What is the value of this transfer function? The second term goes away because S is equal to 0. Right? So this will be 1 upon 1, which is a ratio of 1. So you get 100%, you get all the voltage that was available here. So if your input is Vs at 0 frequency, your output V naught at 0 frequency will be equal to Vs, because this ratio will be exactly equal to 1. Just put S equal to 0 over here and see what happens. Right? So your transfer function at 0 frequency is the full value of the input voltage. You get 100% of the voltage at your output. What will happen at infinite frequency? At infinite frequency, your F is infinite, your omega is infinite, your S is infinite. So in the denominator, you have an infinite term. What would be the overall value of the transfer function? 0. So now you know that your transfer function for this circuit is a function of frequency. At 0 frequency, you have the full voltage. At infinite frequency, you have a 0 voltage. So how does it look like in between? Let's say this is your infinite frequency or a very large frequency. So you know that these 2 points exist. That at very high frequency, your transfer function is 0. At very small frequency, your transfer function is the full value of your a transfer function is equal to 1, which means that the output voltage is same as your input voltage. Okay. So how does it look like in between? What happens if your S is equal to, or if your omega is equal to 1 upon R naught C naught? What happens in that case? You already have this transfer function, 1 over 1 plus S times R naught times C naught. Now, let me write that over here. When your omega is equal to 1 upon R naught C naught, your transfer function becomes 1 plus j omega times r naught c naught, and then now you replace your omega with 1 upon r naught c. So you replace your omega with 1 upon r naught c naught. You get 1 divided by 1 plus j times r naught c naught divided by r naught c. Right? When omega is equal to 1 upon r naught c. So these two terms cancel out. What you're left with is 1 divided by 1 plus j. So this is called a pole frequency. This is the frequency of, this is the definition of a pole, and again, many of you know about this from your circuits 2 class, that at this pole, the value of the transfer function, that is the magnitude of this complex quantity, is basically 1 divided by square root of 1 square plus this other term. Because if you have a complex quantity of 1 divided by a plus j times b, let's say this is a and this is j times b, what would be the magnitude of that transfer function? It would be 1 divided by a square plus b square. In this case, a is equal to 1, b is equal to 1. So if you put a is equal to 1 and b is equal to 1, this becomes 1 upon root 2. Okay, your a is equal to 1, b is equal to 1. So 1 upon square root of a square plus b square, that would be equal to 1 upon square root of 2. So that's the voltage. As we have discussed, that power is basically square of voltage. Right? If you are assuming, why we are saying that power is square of voltage. So power is equal to v squared over r, or power is equal to I squared times r. So you see that the power varies as a square term with respect to your voltage. If your voltage increases 2 times, the power would increase 4 times. If the voltage increases 10 times, the power would increase by 100 times. So power increases as a square term of the voltage. So if your voltage transfer function is 1 upon root 2, what would be the power transfer function? Square of that? Half. So that's why this frequency is also called a half power point. That your original power, whatever power you had at 0 frequency, that will reduce by half at this point, which is equal to 1 upon r naught c naught. So at omega equal to 1 upon r naught c naught, your power will reduce by half, your voltage will reduce by this factor 1 upon square root of 2. And if you calculate this, square root of 2 is 1.414. 1 divided by 1.414 is 0.707. So this value is actually 0. So if this is 1, this will be 0.707, which is nothing but 1 upon square root of 2. So I'm not doing anything special here. So this 0.707, if you just calculate it with a calculator, this is 1 upon square root of 2. So this is called the half power point. So some of you might already know that half power point is the 3 dB bandwidth or the pole frequency of a low pass filter or any filter per se, but we're taking the example of a low pass filter. So that's also called the frequency of the pole. And why is it? What do we mean by poles and zeros in any kind of transfer function? That if you are able to represent a transfer function in the form of, let's say, s plus a times s plus b divided by, again, this is going back to your Laplace transform, which are again not part of this course. We are assuming that you already know about Laplace transform and this kind of transfer function. So if a transfer function looks like this, that you have s plus a, s plus times s plus b in the numerator, and s plus c times s plus b in the denominator. If your s is equal to minus a, if your s is equal to minus a, what would happen to the numerator? S is, just put s equal to minus a in all of these cases. What would happen to the first term in the numerator? That will become 0, right? Minus a plus a is equal to 0. So when s is equal to minus a, that's called a 0 frequency, because your numerator becomes 0 and the entire transfer function becomes 0. Similarly, when s equal to minus c or s is equal to minus d, one of these terms in the denominator will become 0. That's called a frequency of the pole. And that's how the definitions are made, that okay, if your numerator becomes 0, we'll call it a 0. If the denominator becomes 0, we'll call it a pole. So that's the definition of poles and zeros. Now, in this case, you'll see that the transfer function looks very similar to that. So, except for the fact that in the numerator you have only one, and in the denominator also you have only one s term. So it looks like this 1 over 1 plus s times R naught C naught. This is in the form of 1 plus s times, let's say k. Okay, I'm just calling R naught C naught equal to k over here. But this can be written into this form. How? Because your numerator is already 1, so there are no zeros over here. In the denominator, you can write this as s, or you can divide the numerator and denominator with k, and you can write this as 1 over k divided by s plus 1 over k. So this is in the form of this, that okay, you have a constant term in the numerator, there are no zeros in this equation, but there is a pole s equal to minus of 1 over k. And what is k over here? In this case, it is R naught C naught. So that's why your s, which can also be like, if you just figure out the magnitude, you can ignore that j term, and your s will be equal to 1 upon R naught C naught or 1 upon k in terms of the magnitude. So that's why you are calling this a pole frequency. So all these equations will start to make sense if you just go over it again. But and it is provided in the handouts as well. But this is why we are calling this a pole frequency at 1 upon R naught C naught, where the power becomes half or the voltage becomes 1 upon 2 times in the transfer function. So is this part clear in the transfer function? That how we are why we are saying that this is a low pass filter and what is the pole of that low pass filter. Now, if that is true, if you really have this R naught at the output of the amplifier and you have a parasitic C naught, you also have a capacitance at the output of the amplifier, it will not be able to provide the same gain up to infinite frequency. The gain actually will drop and look something like this. So up to the pole frequency, which is also called the 3 dB point or the bandwidth of the amplifier, up to this point, you can assume that your gain is quite high, right? But then after the pole frequency, the gain will drop. And why does it drop? Let's just assume that okay, your frequency increases by 10 times after the pole frequency. Let's say this is the pole frequency. And here the frequency has increased by 10 times because on the x-axis you keep on increasing the frequency. If your frequency increases, what happens to the transfer function? If your frequency increases by 10 times, what happens to the transfer function? The denominator increases by 10 times, which means the overall transfer function reduces by 10 times. Okay. What is 10 or a reduction of a factor of 10 in dB scale? So your voltage becomes 10 times smaller. So your voltage becomes 1 upon 10 times, or roughly 1 upon 10 times, as you increase the frequency by 10 times. So your transfer function becomes 1 upon 10, correct? What is 1 upon 10 in dB scale? You take 20 log of base 10, and then you take this factor of 1 upon 10, right? So what is that value? What is log 10 base 1 upon 10? That is minus 1. So this becomes minus 20. That's why again in books you'll see that they will say that this slope is minus 20 dB per decade. This is the explanation why the slope is minus 20 dB per decade. That you increase your frequency by 10 times, your transfer function will reduce by 10 times. The reduction of a factor of 10 is minus 20 in dB scale. So as you increase your frequency by a decade, that is 10 times, your value of the transfer function in dB scale will reduce by 20 dB. So that's why it said that your slope in this part of the transfer function is minus 20 dB per decade. Question?
So the graph on the bottom there, that's the graph of the gain, right?
That's the graph of the gain. So transfer function, voltage gain, everything is same. Like you might be asked about what does it mean? What does transfer function mean? It's the output voltage divided by the input voltage in terms of the voltage function. What is that? That is gain, the voltage gain. Right? So sometimes you'll see that it's mentioned as transfer function in some books. Some books will call it voltage gain, some books might call it just gain, but it all means the same thing.
What is the bar? Is it x-axis or
That is frequency. The x-axis is frequency.
is it on a log scale?
You can create it on a log scale. Right? What I'm drawing, this is a cartoon diagram. I haven't drawn it to scale. This is just a cartoon diagram, but you can draw it on a log scale, which will, even in that case, it will look the same. Yeah, it's just that it will be compressed if you draw it in a log scale. Okay, so, but the bottom line is that if you are increasing the frequency by 10 times, your voltage transfer function will reduce by 20 dB after the pole frequency. Before the pole frequency, it will remain almost constant. So this is called a first order low pass filter. So now with this idea in mind, let's see what we have in the handout. So a low pass transfer function, when you have a single pole, that low pass transfer function is A of, now you already know that j omega is basically your S, and omega is equal to 2 pi times F. So in this case, we are just referring to it as a function of j times F, or basically a function of frequency, and that will be given by A naught divided by 1 plus j times F over Fp. How does this equation come in? This equation comes in because, can I erase this? Or maybe I'll just erase some part of this. Let me just erase this part. Okay. So what we are saying is that my transfer function is A naught. Till now, you have only considered A naught, which is the gain at zero frequency. Let's just assume that this is the gain at zero frequency. That's why we call it A naught. But it has a frequency dependence. And the frequency dependence comes because of all these things that we have discussed earlier. The Fp is the frequency of the pole, and F is your frequency that you are switching. That from zero frequency you're going to higher and higher frequency. So what this really says is that your transfer function is A naught divided by 1 plus A times F over Fp. Now, why we are saying that it is same as this transfer function we have written over here? It's because let's just multiply this F with 2 pi, so you will get 2 pi F. Let's just multiply this Fp with 2 pi, so that you will get twice pi times Fp. So what is 2 pi F? 2 pi F is omega. Angular definition of angular frequency. Again, going back to high school frequency. Angular frequency is twice times pi times F. So this is A naught divided by 1 plus j omega. And what is 1 upon twice pi Fp? So 1 upon twice pi Fp, while Fp is the pole frequency. So this is equal to 1 upon omega p. Right? Again, you can write omega as 2 pi f and have the same subscript. So this is equal to 1 upon omega p. What is omega p? Omega p is the pole frequency, which in this case you found out as 1 upon r naught c naught. So if omega p is equal to 1 upon r naught c naught, what is 1 upon omega p? That is equal to r naught c. Okay. So you have A naught divided by 1 plus j omega times r naught c naught. Because this 1 upon omega p was multiplied with your j omega. We are just using this value over here. Okay. Now your S is equal to j omega. This becomes A naught divided by 1 plus S times R naught C naught, which is same as this form, right? The low pass filter that we have solved. The only difference is that here in the numerator you have A naught, because of course your amplifier has a gain. In this case, this circuit did not have a gain. The best gain it can provide is equal to 1. This does not have a voltage gain. This is a passive circuit. On the other hand, the amplifier is an active circuit. It can provide an active gain of A naught. So that's why your numerator is A naught, but the denominator looks exactly the same. So this form that you see on the board and the form that you have in the handout is exactly the same. Why we are representing it like this? Because here you have a very good idea about what is the gain of the amplifier and what is the pole frequency of the amplifier. Right? Even though what we are drawing in the board, that like doing the mathematical calculation was easy over here, but you just represent this term as something like this because you have all the information over here, that what is the amplification factor at zero frequency and what is the frequency of your pole. That's all you need for a first order low pass filter. For a first order low pass filter, you have this gain of A0 at low frequencies. Of course, the gain will start dropping a bit and you have your minus 3 dB point over here at the pole frequency. But ideally, it is like, to simplify things, it is assumed that, okay, your gain will be A0 up to the pole frequency, and then it will drop with a slope of minus 20 dB per decade. So that slope is minus 20 dB per decade. So even though the actual curve will look something like the yellow curve, but for simplification, you can just assume that, okay, this somewhat looks like a blue curve with this much amount of error around the pole. What is the magnitude of A then? The magnitude of A will be equal to A0 divided by square root of 1 plus F over Fp whole square. Again, this comes from your complex number theory, that, okay, if you have a A0 divided by A plus JB, if that is your complex number representation, what is the magnitude of that gain term? That would be A0 divided by square root of A square plus B square. That just comes from your complex number theory. So that's the magnitude of your gain as a function of the frequency. So of course, if F is much smaller than Fp, let's say your frequency is much smaller than the pole frequency, what would be the magnitude of the gain then? This factor of F over Fp will be very small, and the square of that will be even smaller. Let's just assume F over Fp is 0.1, that your frequency is 10 times lower than the pole frequency. Square of that will be 0.01. Right? Square of 0.1 is 0.01. So you add 1 plus 0.01 and take the square root of that. So effectively, you have a denominator which is equal to 1. So your overall transfer function, value of the transfer function will be A0 if your F is much smaller than Fp. At F equal to Fp, the value of the transfer function will be A0 divided by square root of 2. The same calculation I have done on the board. Right? And it comes from this A0 divided by A square plus B square. Both your A and B are equal to 1. So A square plus B square is 2. And you have that under a square root term. So your value of the transfer function is A0 over square root of 2 when you are at the pole frequency. And if you convert this to dB, decibel, this is a minus 3 dB point. Because just like we converted 1 upon 10 in decibel and got minus 20, if you convert 1 upon square root of 2 in decibel, just do it in your calculator when you go home, and you'll see that 1 upon square root of 2 is minus 3 dB in decibel scale. So what I'm saying is 20 log base 10 of 1 upon square root of 2 is equal to minus 3. It will be minus 3.0 something, but for all practical purposes, you can assume it to be minus 3. And if your F is much higher than Fp, if your frequency is much larger than the pole frequency, your transfer function, in this case, the magnitude of the transfer function, if your F is much larger than Fp, you can write it as A0 times Fp divided by F. Why? Because again, see, your F is much larger now. So F over Fp, that ratio will be much larger than 1. So you can ignore this one term. And since you're taking the magnitude, you can ignore the J term. What will be left with is A0 times Fp in the numerator and only F in the denominator. That's what we wrote over here. A0 times Fp in the numerator and just F in the denominator. And because you have f in the denominator. So f increases by 10 times, your transfer function reduces by 10 times. That has a minus 20 dB per decade slope. So that's just repetition of what we have done in the board. But now I think you'll get a better idea how these numbers come in. What would be the phase of the transfer function? What would be the angle of A? Again, going back to your theory of complex numbers, high school math, that's tan inverse of the imaginary part divided by the real part. What is the imaginary part over here in this transfer function? This is the j times f over fp, right? So that will be the imaginary part, j times whatever is multiplied with j, that is f over fp. And what was the real part? The real part was equal to 1. So that's why the real part is 1, imaginary part is f over fp. But because that 1 plus f over fp, the entire thing is in the denominator, you have this minus term. If that real and imaginary would have been, so you can just convert this to something that has a fully real part in the denominator. So what you'll do is that you'll multiply a naught with 1 minus j times f over fp, and you'll multiply with the same thing in the denominator as well. So in the denominator, you'll get something that is fully real. That would be 1 minus f over fp whole square. Once you do the calculation, because this is a minus b times a plus b in the denominator. So your denominator will become fully real, your numerator will become this. Take the angle of the real and imaginary parts, you'll see that you'll end up with this minus tan inverse of f over fp. But a quicker way to remember is that because this is in the denominator, you take the imaginary and real part from the denominator and put a minus sign. That's it. And again, if you do the same thing for f much lower than fp, f equal to fp, and f much higher than fp, you'll see that 0 degree when f is much lower than fp. So f is very small, your numerator is very small. So the tan inverse of almost equal to 0 is 0 degree. When f is equal to fp, your numerator and denominator are equal, you have a tan inverse of 1 with a negative sign. What is tan inverse of 1? 45 degrees or pi over 4. So this is minus 45 degrees because of the original negative sign or the minus sign in the beginning. When f is much larger than fp, you will have minus 90 degrees because you have tan inverse of infinity. F is much higher than fp. Let's say f is infinitely larger than fp. So you have tan inverse of infinity. What is minus tan inverse of infinity? Minus 90 degrees. So whenever you have a pole, this is how the phase looks like. You start from 0 phase. At the location of pole, you have a 45 degree phase shift. And at infinite frequency, you will have 90 degree phase shift. Or at very large frequency, you'll have 90 degree phase shift. So that's how the phase looks like. And we have already seen how the gain plot looks like. So these are the two most important takeaways when you are doing a frequency response of an amplifier. That usually you'll consider this as a single pole low pass filter, because at the output you have that R0, the output impedance of the amplifier, and you'll have a parasitic capacitance anyway. And if not a parasitic capacitance, you'll connect this amplifier output to some input. Let's say you connect it to another amplifier. So you are talking about two-stage amplifiers, right? The other day. So what you do is that you have one amplifier connect the output to the second amplifier. The second amplifier will have an input capacitance. So that's how you'll always have this parasitic capacitance C0, and that C0 along with your R0 will provide this low-pass filter response. Question?
Is that C0 the value of that capacitance? Is that determined just by the individual op-amp frequency?
Yes. So an op-amp. So if you look into the data sheet, that op-amp will show that how much input capacitance does it have, and that will be your parasitic C0. Now that parasitic C0 can vary. Even if they mention that okay, the parasitic is only 1 picofarad or 2 picofarad, that will be the ballpark range where what you will see in the data sheet. But if you want to control it, you'll put some additional amount of capacitance over there. Let's say you put a real 10 picofarad over there so that you can control the bandwidth with more precision, more accuracy. Yeah, because if you just rely on the parasitics are not that reliable, that it can change from one op amp to another, or it can even change with time if it is a dynamic behavior of the parasitics. All right. So how does it change our analysis of loop gain? So I'll upload your homework 3 today, and that will be due next Friday. Actually, next Friday is your homework, is your exam number 1. So exam number 1 will contain all these analysis that we have done with respect to voltage division, current division, op amps, non-ideal op amps, and the frequency response of op amps. So it will contain all these discussions. We'll also cover diodes before your exam, but diodes will not be part of your exam. So in the exam number 1, we'll only consider voltage and current divisions, ideal op amps, non-ideal op amps, and frequency response of op amps. So we have already analyzed ideal op amps and non-ideal op amps. How does this idea of frequency response change your analysis of non-ideal op amps? You already know that you represent you can represent the gain as a function of frequency. So you represent your gain as a function of the frequency. What would happen to the loop gain? What would happen to the loop gain T, which is equal to A times beta? The loop gain will also become a function of frequency because A is now a function of frequency. So that's the only change that is happening. That instead of your gain and loop gain independent of frequency, instead of being a constant value, now both A and A times beta, which is equal to your loop gain, both of them are a function of frequency. And how does that function of frequency looks like? For A, it's A0 divided by 1 plus JF over, let's say, FP or F1. I think there is a, here we are calling it FP, but from this point onwards, like it's written as F1, but it's basically your FP, the pole frequency. Yeah. So A0 divided by 1 plus J times F over the pole frequency, that's your transfer function, that's your frequency response of the amplifier. How would the loop gain look like? The loop gain will be that frequency response of the amplifier multiplied with beta. Now, beta is just a ratio of resistances, as we have seen in homework number 2. Now, if you have a ratio of resistances, that's not frequency dependent. Only if you have a resistance and a capacitance, it becomes frequency dependent. So beta is not frequency dependent quantity. Beta is just a ratio of resistances, which will be same for all frequencies. So what will change here is basically instead of just calling the loop gain as equal to T, you will have P as a function of frequency, and it will also look very similar to how your A looks like. So it will be T0 divided by 1 plus J times F over F1 or Fp. This is basically the pole frequency that we have been talking about. So, and of course, you know that your T0 is much, much larger than 1. What is your closed loop gain? What is the closed loop gain is A infinity divided by 1 plus 1 over T. Now, instead of saying that, okay, my T is a constant quantity, you'll consider that as a function of frequency. So in the denominator, it would be 1 plus, instead of just 1 over T, it would be 1 over T of J times F. So you're actually representing T as a function of frequency. That's it. That's the only change you'll make in the entire analysis. Why? Because A infinity assumes you have an ideal amplifier. Just like an ideal amplifier had that infinite input impedance, infinite gain, and zero output impedance, you'll assume that it has infinite bandwidth as well. Or it will actually be given in some problems that what would be the bandwidth of this ideal amplifier, and then we'll consider that bandwidth of the ideal amplifier. But what really changes from the previous analysis that we were doing is that this T will now become a function of frequency. All right. So if you just write that down, your A of JF. So let's say this is the closed loop gain of the system. The closed loop gain of the system is A infinity divided by 1 plus T of JF. 1 plus 1 over T of JF. Now, what is T of JF? It's T0 divided by 1 plus J of J times F divided by F1. So you just put that value over here. So this is just T of frequency, T as a function of frequency, or basically 1 over T as a function of frequency. Okay. Now this, because your T naught is much larger than 1, your loop gain is much larger than 1, as you have seen in the homework number 2. That if you multiply A with beta, you'll still have a quantity which is much larger than 1. If T naught is much larger than 1, what will happen to this quantity of 1 over T naught? That's very small. So you can just ignore it. Again, for practical designs, you can just ignore which is very small. So 1 over T naught, this term will go away. What you will be left with is just J times F divided by T naught times F1. Okay, I'm just removing this 1 over T naught term. So you have J times F divided by T naught times F1, where F1 is your pole frequency of the original amplifier. So this is how the original amplifier looked like, that at F1 you had a pole. Now this you can write as A infinity divided by 1 plus J times F over F gain bandwidth product. Why are we calling it the gain bandwidth product? Because this is T naught times F1. So gain bandwidth product is basically T naught times F1. That's what we have replaced here in the previous equation. So what is T naught times F1? You already know T naught is A naught times beta. So A naught times beta times F1. Okay. And A naught times beta is the gain. It's basically how T naught looks like in the closed loop transfer function. So that's the low frequency gain, low frequency open loop gain is T naught, which is equal to A naught times beta. What is the bandwidth? The bandwidth is still F1. So gain, which is A naught times beta or T naught, that times the bandwidth, we'll call that a gain bandwidth product. So it's just multiplication of gain and bandwidth that gives you the gain bandwidth product. So in a closed loop scenario, the gain bandwidth product is A naught times beta times F1. But F1 is the pole frequency in the open loop scenario. Okay. But now this also if you go back to the previous equation, so this is what we have written as closed loop A, the closed loop gain as a function of frequency, and that looks like this equation, that A infinity divided by 1 plus J times F divided by F GBW. This looks very similar to this form, right? A naught divided by 1 plus J times F over FP. This was the open loop transfer function of the amplifier. So if you just consider the op-amp, the transfer function of this I'm drawing the simplified form. So it's constant up to the pole frequency, and then it drops by 20 dB per decade, minus 20 dB per decade. So this frequency is FP, if your x-axis is frequency. And this value is A naught. The highest value that you have is A naught, right? So that was for the op-amp in an open loop configuration. Whenever you have the op-amp in the closed loop configuration, you still have a very similar form over here. You have A infinity divided by 1 plus J times F over F GBW. In the previous case, it was A naught divided by 1 plus J times F over FP, and we call this FP as the open loop bandwidth. So what is your closed loop bandwidth? Your closed loop bandwidth will be F GBW. And F GBW is T naught times F1, which is A naught times beta times F1. So just keep this, think this in a clear mind, that which quantity we are talking about in open loop and which quantity we are talking about in closed loop. In open loop, we are only talking about the op-amp, and it has a response that looks like this. When you put this in closed loop, you have an equation which looks very similar to the previous one, but it's just that it has a it has a low frequency gain of A infinity. So the closed loop bandwidth or the closed loop response will also look very similar. It has a closed loop gain of A infinity. Instead of having an open loop, in the open loop case, this was A naught. And remember that A naught could be very high. A naught could be 500, A naught could be 1000. That's a gain of your op amp in an open loop scenario. That you're just talking about the op amp. You're not talking about any feedback or you're not talking about any closed loop application. In the closed loop scenario, your gain becomes A infinity. Something that you have already done in your homework number 2, or you're doing in your homework number 2. That your gain has become A infinity. And your bandwidth has become A naught times beta times F1. In the open loop scenario, your gain bandwidth was A naught times F1. Here, it has. So what we are saying is, if you draw the open loop scenario and the closed loop scenario side by side, this is how it will look like. So let's say this is your open loop condition that you have A naught and you have FP or F1. That's your pole frequency. In a closed loop scenario, your gain will reduce. So your gain will be somewhere over here. And this will be your FGBW. Or basically this T naught times F1. So effectively, you'll see that your DC gain or zero frequency gain reduces by T naught times, and your bandwidth increases by T naught times. So there you'll see a reduction in gain, which you have already seen in your homework number 2, but your homework number 3 will be the increase in the bandwidth. So your gain bandwidth product will remain same. So you might have heard about this as well in your circuits 1 class, that the gain bandwidth product of the op amp remains same. This is what we mean by that the gain bandwidth product will remain same. Your gain will reduce by, let's say, T naught times when you put it in closed loop. Your bandwidth will increase by T naught times when you put it in closed loop. So the overall product will remain same. Okay, just go over this equation, these equations. It might again sound confusing at first, but this is the gist of it. That this is your open loop. What I have drawn in red is open loop. What I'm drawing in blue is closed loop. So in open loop, you had a DC gain of A naught and a pole frequency of F1. In closed loop, you'll have a DC gain of which is reduced by T naught times, but a frequency which is increased by T naught times, which is evident from this equation. Right? Directly from this equation, we can say that your bandwidth is increased by T naught times, because this is what you have in the denominator over here. That's your pole frequency. This is T naught times F1. In the previous case, it was just F1. In the next class, we'll solve a problem, or maybe 2 or 3 problems, which will give you a better idea about how to solve the frequency response related problems for homework 3.